So hopefully I am live. I shall just wait and see if we get anybody in. Now Nathan's just been live. Unfortunately, I wanted to do this presentation on his particular channel, but I never got the opportunity to because Timmy Osmond came in and decided to be a bit of a mic hog, really, and waste everybody's time with old, tired 2015 rhetoric that has been thoroughly debunked. Anyway, I'm just going to wait until we get a few people in. Oh, They Lie Ohio is first. Actually, funnily enough, you being the first person in right now is exceptional coincidence, really, because I am going to be including an observation from Hawaii, and funnily enough, if you just want to actually confirm right now that when you were in Hawaii, you lived in Hawaii, you actually saw bulging of the water. You actually saw the water higher than your feet were at the seashore. If you could confirm that right now, it will just add to the presentation. In any event, Ragnar Stafford Hallardson, nice to see you in. Jimbo, nice to see you in. A classic show. FED, Timmy was shameful. Timmy was, it was desperate stuff. We're in 2020 now, and man, he's bringing up arguments from 2015, 2016. Mark Collard, nice to see you in. Individual one, nice to see you in. And They Lie Ohio, who actually, believe it or not, guys, is actually a globe earther, has just confirmed that yes, he actually did. He did actually observe this phenomena. Super Dave, nice to see you in. Great streams that you keep doing, keeping people busy. Right, okay, so we've got a few people in right now. So I'm going to start with this little bit of a presentation. So TG1210, nice to see you in. What does that say? Good morning from Cleveland, Ohio on Flat Lake Erie. I'm currently watching waves hit the break wall downtown from 12 miles west, super looming hyena. I hope you're recording it. I hope you're recording it. Maybe you'll be putting a video out about it. Who knows? Anyway, I wanted to firstly talk about the globe logic and what globe earthers want flat earthers to do when they talk about observations and such. So here we go. So we have a body of water separating these two individuals. They're both looking at each other, and this is the globe logic. Globe logic says you could put these people at 100 miles apart and you would still see each other. It doesn't matter. And look at the water. Look at the water between point A and point B. It's completely flat. So this is what globe logic wants you to do when you're doing your observations. They want to say, well, you live on a flat earth, flat water always finds its level, yeah, so it's got to be flat, yeah, and that's what they will tell you. And they will want to know how far above sea level you are. So they will want to know, if you're doing an observation, they'll want to know where your feet were in regards to the water, and then how high up you were, your eyeball or your camera, you know, above the water's edge. That's what they want you to do. So if you've got your camera set up to, let's say, 4 or 5 feet right next to the water's edge, they want you to put in 4 or 5 feet above actual sea level. So that's what they want you to do. That's what they need you to do, because in a moment when I get around to explaining what happens in reality, you're going to understand that this globe logic and them wanting to put you on the surface like this is what they need for their calculations that quite often fail, bearing in mind, but they need this, and we don't need that. We need to apply real world issues that go on when you're doing these kind of observations. So let's move on to the next slide. So here's globe logic. Globe logic says that if you live on a flat earth, water finds its level, it's flat, and you should be able to just see the entirety of people on distant shorelines, buildings, doesn't matter, because this is the diagram they want you to work with, right? This is how they need you to portray a side-on view of you observing somebody over some water. So what we're going to do now is we're going to add some real-world obstruction that is not earth curve, right? So obviously, what could that be? Well, you could have a boat, I suppose, that passes by. A boat could get in front of your view from person to person, in which case you would have a boat blocking your view, so you wouldn't see that. But for this case, we're just going to stick to reality and shoaling. So I'm going to get into this shoaling in a minute. And what we're looking at here is we're looking at the topography of the land underneath, which you can see is something like this, relatively flat, and then a sort of a runoff, a slope, going from the deep water into the shallow water. And in these two locations on each side, you do get this effect called shoaling. Now then, what I've found more recently, and I did start looking into this about a year ago, and I put plenty of videos about shoaling. However, I never actually found all the information that I've been looking for until when I started to look into it again in the past week. And it's amazing how suddenly all this information's out there, because when I was talking about this, I couldn't find it. There wasn't a lot of information out there. There wasn't a calculator I could find. There was nothing that I could find to explain what I was trying to present. But now it seems that this information is there. It's available to be found. So let's have a look at some of this information, shall we? So going up to nature.com, and we're going to look at a typical example of a beach system. Okay, so what you have here is the shoreline. Can you see where it points to the shoreline, and it has a little wave cresting over called the swash zone, so right at your feet where the wave's lapping up. It also has a channel and the bar that comes down here, and you've got the wave base here, etc. And what you have here is you have this near shore zone wave shoaling, and it gives you this example of wave shoaling here. And as you can see, there's quite a substantial wave here in relation to the shoreline, and it's far bigger than the actual wave that's crashing up at the shoreline. Now that's important that they've actually put this in, because that is reality. That is reality. Let's go over to sciencedirect.com, which talks about physical environment of tides, etc., and shoaling. It goes on to explain landward of the breaker zone, these beaches are dominated by surf and swash zone processes. As tide range increases, the impact of both the swash and the surf zone process decreases, and shoaling waves become more important. Okay, going on to shoaling waves. In general, waves that are generated as a result of a distant storm or localized wind event propagate and disperse relatively unhindered until they encounter shoaling water. At this stage, two processes influence waves: shoaling and refraction. Not refraction as in visual refraction, but refraction of the water in the topography of the area. Going on to what is wave shoaling. Shoaling is the process by which the wave height, length, celerity and other properties of the waves change as they travel from the deep water to the shallow waters. So I think we're pretty concise here in explaining what this shoaling does. Basically that's the movement of the water from the deep to the shallow, up the slope, and obviously it gets to a point where it just has to go up, it has to raise in height. So calculations, we can calculate this. Let's get a calculator. So here we go. So this is the shallow wave calculator, and basically we can use it to find out how high this shoaling process will be when we're trying to do observations. So the company that's actually made this, if we open that in a new tab so that you guys can see that I've not altered anything, it is the University Corporation for Atmospheric Research. serving the Earth system science community, etc., etc. UCAR manages the National Centre for Atmospheric Research on behalf of the National Science Foundation, etc., etc. So these are the guys that have produced this calculator. So let's go over and look at Shoaling. So it gives you different topographies to consider when you're actually trying to work out what the wave heights in certain locations will be. So on a gentle beach, you've got a 1 in 50 slope. A moderate beach is a 1 in 33 slope. An average beach would be 1 in 20 slope, and a steep beach would be 1 in 20. So let me get up Google Earth. Let's bring up Google Earth, and we'll go to Hawaii, and we'll have a look at this before we put any calculations in. Right, let's go to Hawaii. Right, let's go to Hawaii. Let's have a look over here. And this is why I was glad that they lie Ohio's in. So here we have Hawaii. So let's just come down here. Let's just go to, I don't know, let's go to this place, this location over here, this Kailua, Kona, something like that. And what we're going to do now is we're going to do a measurement. Let's go in meters, and we're going to say from the beach, basically, from this location here. Let's go out 3,000 meters or so. So there's 3,000 meters, basically right there. Come down here, as you can see, and what you're going to be looking at here is you're going to be looking at the elevation down here, the elevation process right at the bottom. I don't know if you can see it on this. You can't actually see it. I've not got it set up correctly, but it's minus 322 meters here, and basically it's 3,000 meters or thereabouts, which is about a 1 in 10, which is about a 1 in 10 slope. So from the deep slope here, minus 300 meters, coming all the way up to the shoreline to 0 meters, it's a 1 in 10 slope. So that's quite a severe slope in Hawaii, and you can see that by the color of the oceans. Google Earth is quite good at actually showing you these depths. The darker it is, the deeper it is, and the steeper the runoff. So from the shoreline to about 3,000 meters out, it goes off really steeply, and you have a quite a severe drop, about a 1 in 10. So let's go to this wave shoaling calculator, and we're going to look at the Hawaii surf reports for today. So let's come down here. Let's go to Kalahulu, which was probably near to where I actually was just then. So the primary swell is 4 feet, and it's every 14 seconds. So you can put this into the calculator. So you can put 4 feet every 14 seconds, and you can calculate it. Now then, let's come down here. So the breaker height, I don't know if I'm just making sure that we can actually see this on the screen as well. I think we can. It says the breaker height spectrum. So 1 in 10 waves, 1 in 10 of these waves, bearing in mind that it's only 4 feet high. It's only 4 feet high, and we're only working right here on a moderate beach. So this is a moderate beach, a 1 in 33 slope. It's not going down to the 1 in 10 slope in Hawaii. It's not doing that, it's doing the moderate beach. So 1 in 10 waves will be 10 foot and 10 foot 2. 1 in 100 waves will be 14 foot 3. And it will have a maximum throughout the day. There will be times that it reaches 16 feet in height. So that's just on a moderate beach, right? So on a moderate beach with a slope of 1.33, this shoaling effect with a wave height of 4 feet, a period of 14 seconds, the height of 1 in 10 waves will be 10 foot 2, right? So how does that work out? How do characteristics of a wave? Let's have a look at these, shall we? Let's go to, don't want to open it in Paint. I want to open it with photos. So here we go. So what is a wave height? So it's basically the amplitude of the wave is everything above flat. So if there was no movement on the water at all, this line in the middle, this completely flat line here, would be the mean sea level. So the amplitude, and you've got the trough. So that is the top of the wave to the bottom of the wave. That is how you measure the height of the wave. So if this was the wave that we're trying to measure, and we're told that there's a 4-foot wave, because that's what Hawaii has right now, so it would be from the top of the wave to the bottom of the wave. Now that would be 4 feet, which means when your little tootsies are at the shoreline here, your tootsies, I wonder if that's on the next image. I might have that on the next image. Let's see if I can bring it up. Let's see. Yeah, here we go. So your feet are at the shoreline here. You've got the wave that's going up. This is about a 2-foot obstruction. I know it's not to scale. And then as it comes down, you've got another 2 foot here. However, when you start including the shoaling effect, what it's saying is that 1 in 10 of these waves where it shoals will be 10 foot too, which means that'll be 10 foot too from the top of the wave to the bottom of the wave, which means that the height, the amplitude of the wave will be over 5 feet in height where it shoals, right? It also goes on to say in the calculator that 1 in 100 of these shoaling waves will be 14 foot 3. 14 foot 3, so you're a human at the shoreline, 14 foot 3, it's at least 7 feet in amplitude. 7 feet, 7 feet. And this is a calculator that can be used to work out things like this. Distant boats. Here we have a boat in Hawaii. Now this was taken from, let me see if I think he's BM Furball. Let's see if I've got his up. Yeah, so this is from BM Furball. Now he put a video out called Hawaii Updates. And this video, to me, this image stuck in my mind because clearly he's on the shoreline taking an image of this guy who's actually in focus. And behind him he has a boat. And the boat looks like it's sinking. The boat genuinely looks like it's sinking. Half of the words are missing. And to me this didn't make any sense because you can't have a guy in focus and the boat is pretty much in focus too. It's not like they're out of focus. He can't have, this guy can only be 100 feet away at most. This boat can only be a couple of miles away at most. Everything's in focus in this image apart from these people on the right hand side, but the boat's in focus, the human's in focus, and yet the boat looks like it's sinking. And this image bugged me. It really, really bugged me until I started looking into shoaling. And this is the effect of shoaling, especially in places like Hawaii. What you have is you have a boat that's beyond the shoaling range, a couple of miles away. The shoaling effect has already taken place. And the waves that you're actually seeing here, these waves on this particular day, gave you the effect that the boat was actually behind Earth curve, even though it's impossible for it to be Earth curve because this boat can only be a couple of miles away. But this shoaling effect, is giving you an optical blockage. Now, that can be demonstrated, as I say, that it can be completely demonstrated when you take this shoaling into effect. If we was to give, let's have a look at another place in Hawaii. Let's try on the other side. Let's go over here. So we've got 5.5 feet every 10 seconds. Let's put this calculation in. 5.5 feet. 5.5 feet every 10 seconds. So calculate that. Now this is a 5.5 significant height of the wave is only just under 3 feet above, the shoreline where it breaks here. It's only 3 feet. However, 1 in 100 of these waves is going to be 13 foot 7 when you include the shoaling, which means that over 6.5 feet is going to be physical obstruction. So going back to these kind of observations here, when you're trying to see each other, and obviously this is when you've only got 3 feet of shoaling, you're looking into the waves a little bit and it's obstructing somebody. This is putting reality into things. But what happens when you put 10 feet of shoaling in the way? And I know it's not to scale, but this effect where it shoals and you're at the shoreline with your feet here, you're a 6 foot human, you're looking over the waves, you're looking over this shoaling effect. You're never going to see the other human on the other side. You're never ever going to see that. But yet the Globers will want to put you in this position. This is what they want you to have. They want you to have a flat surface without any movement of the water whatsoever. But we can demonstrate, because there is science out there that works for the good, we can prove this. You can't prove looming, but you can prove that the shoaling happens. You can prove that the physical obstruction, just like this, will get in your line of sight. And you will have to look over waves, especially in places like Hawaii, Australia, New Zealand, etc. It's only when you get to places like where the Red Pill Philosophy films and myself, so let's have a look at where I live. Let's go to the Blackpool, UK. So when we go to places where I live and I do these filmings over here and we see shore to shore, you can already see the colour of the water is a very light blue. And this entire area doesn't go very deep at all. It's minus 2 meters, minus 2 meters, going down to about minus 15 meters or so along this line of sight. It's not a huge drop off. And this area stays consistent all the way around. It's a very low-lying, flat underwater topography. So we don't get an awful lot of shoaling here. You know, we're on the minuscule side of things. Red Pill Philosophy, when he did his video, he also, when he filmed it, it was just minus 1, minus 2, minus 1, minus 2, all along that stretch. So it didn't have a lot of topography that was manipulating the water. But when you go to places like Australia, New Zealand, as I say, and there's a lot of globe earthers down there, because when they go down to the beach, they encounter this obstruction. They see boats in the distance that are hidden from the hull up, and you know they'll come back and they'll say, well, that's proof of looming, yeah? Sorry, proof of curvature, yeah? But no, it's not. So here's the human on the shoreline. Here's the surf and the swash zone. So obviously you're getting your 2 and 3 foot waves lapping up on the shoreline, physical obstruction anyway. Then you get into the shoaling zone where the waves are much higher, right? So the waves are much higher in the shoaling zone. Let's say a mile offshore, 2 miles offshore, you've got this shoaling zone. Now the waves are 6 foot high, right? The human at the shoreline and the shoaling zone, the waves that are crashing up here, they're also 6 feet. And the human is looking out and he's thinking, oh, I see a boat in the distance over here. Now, once you've gone past the shoaling zone, the waves peter off again because they're not having that effect of having to force them higher. They go back to the normal swell, the 3 foot, the 4 foot. And you've got the boat in the distance here, beyond the shoaling zone. And that human's looking out and he's saying, I see obstruction. I see obstruction like this. I see, when I look out, I'm looking across these waves and I'm seeing this boat in the distance and its hull is missing. The bottom of the boat is missing. It's gone. And they will say that's proof of curvature. No, it's not. It's proof that what you're actually looking over is areas that will cause physical changes to the water to force them up. They will be forced higher. It's just the way nature works and reality. It's just what happens. So my whole point in this presentation is that you don't want to stick to this kind of side-on view that these globers will have you try to work with. They will try to put you in this position where you're just looking across a flat, stationary, immovable water like this. They don't realize that the water's dynamic, it's changing, it's moving, it's a rolling deck. It rolls and moves all the time. And the water is affected by the topography of the land. So if you want to use this calculator, you can find it on here. It's at comet.ucar.edu, or you can just look in for Shoaling calculator. And when I did it a year ago, I couldn't find it. They weren't giving me these results. So I mean, it's possible that this was up for many years, but for whatever reason, last year I couldn't find this stuff. Now it's out there. Now we can find it. Let's try one more. Let's go to I don't know. Let's try this guy. Let's see what the shoaling effect is at Barber's Point right now. So we've got 2.5 feet at every 14 seconds, which is basically only 1.5 foot of amplitude, 1.25 foot of amplitude if you was just measuring it on the primary swell without actually taking into effect this shoaling effect. So let's put 2.5 at 14 seconds. 2.5 at 14 seconds, and let's see what that effect does. Let's calculate that. So 1 in 100 waves, you're going to have 8.8 feet. 8.8 feet. Even though if you was just measuring it by amplitude alone, it would be 1.25 foot. But you're actually going to have 8 foot 8, which is about 4.4 feet. 4 times the obstruction by the shoaling effect. So understand the topography of the area that you're filming in. Understand that, you know, in the UK where we've got lots of flat earthers doing great stuff, great video photography, we can see shore to shore in a lot of these places, and that's because we don't have these great drop-offs like here. You see these drop-offs here. But in places like Australia and New Zealand, if you're an Australian and a New Zealander, you know, you've got to look into these effects. You've got to understand that, you know, there's probably a good reason why you can't see those boats in the distance. Those boats in the distance are most likely, they are hidden behind water, physical water, but it's the shoaling zone that's causing this. Right, okay, let's see how the chat's going. Pop out the chat and I'll drag this over here and let's see who we've got in. Right, who do we have in? Let's see, we got Tim Osman. How much shoaling should I expect at the Great Salt Lake? Tell me. You probably won't see much, but you probably will see a lot of inferior mirage. Who else have we got in here? Rakia Life, nice to see you in. MiG-13. Oh, and going back to They Lie, Ohio. Yeah, I mean, this is just perfect. This observation here, this Hawaii, this observation here that befuddled me for the longest time, looking at this observation and thinking, well, clearly he's about 6 feet above sea level anyway, because he's taking the image, he's on shore, he's filming this guy, you know, level with his shorts, and the boat looks like it's sinking. You know, the boat looks like it's sinking. But this obviously explains it. Put the boat 2 miles away, it's still in focus with the human. You've got this shoaling effect in Hawaii that happens because you've got a 1 in 10 drop off. So even a 2 or 3 foot height shoaling effect swell is probably going to create a 10, 12, 15 foot shoaling effect near the shoreline. That will artificially increase the height of the water. So that boat in the distance is just the same as this image that I've got up on screen here. This one. So here he is, he's looking out, he's trying to see that boat in the distance. Half of it's hidden behind this shoaling zone, and the boat itself is out of the shoaling zone, so it is lower in the water compared to the shoaling zone that's actually causing a physical blockage here. Right, who else have we got in? Let's see. Smithy 008. Oh, so yeah, so here we go. So this was another point that I wanted to talk about. Sandra Woods, nice to see you in. What happens next? So what comes next? So obviously you've got this shoaling zone, right? So you will see boats and you will see them hidden by physical water, physical obstruction. It will happen. But what will happen then? Well, the Globers are going to now come back and say, well, you need to go higher to get over the shoaling zone. Makes sense, right? Yeah, it does make sense. Go higher, go higher. But what happens when you go higher? And then you've got a new calculation then to put in. You've got a new calculation to put in because now you have in the globe model, a further horizon, a further distance. So let's suppose, well, let's get a curve calculator up, shall we? Let's go and put a curve calc up. There we go. Let's get this curve calculator up. We'll go to Mick West's keep going to Mick West, so I always go to his. So let's give us a height. So we're going to go to a height. Let's go to, I don't know, let's say, go to 25 feet. Right, so now we have a horizon that's 6 miles away. Yeah? And we know that we can see much further than 6 miles. But you run into problems once you go to these sort of elevated heights. The problem is that you're now looking through the air. And the air has things in it. You know, your nose has hairs inside to capture those things. Dust, dirt, pollen. That's why when you've got hay fever, it's because your nose captures these things. It's designed, it's a filtration system. It filters out the air because obviously you don't want crappy stuff going in your nose. There are particles in the air that cause blockage. There is all manner of things in the air that stops you seeing a certain distance on any given day. So, and it's called visibility. So you can check it on the weather. So let's see, weather Blackpool. There we go. So let's bring up, hopefully we'll have something that has a visibility in. Let's see if this has visibility in. Visibility, it's not put in its visibility today, but it might be on another one. Let's look at AccuWeather. Let's see if this has visibility in it. Right, let's see. Let's click on this. Just bear with me, guys. Visibility, here we go. So here we have a visibility, 16 kilometers. That's what it tells me, that in Blackpool, your visibility is 16 kilometers. So essentially about 10 miles. That's your visibility today. You can't see forever. Let me increase that so that you can all see that I'm not actually making that up. Where's it gone? Yeah. Visibility, 16 kilometers. There we go. So that's how far we can see today. Right now, we can see 15 kilometers. We also have a bit of rain going on, right? So there's a bit of rain dropping around. And you know when it's raining, you can't see very far. So your visibility is always determined on a particular day. And a lot of things can affect that, right? There could be pollen in the air, dust. There's obviously you've got other things to consider, which is evaporation over the water. You know, as much as it rains down, the water's still going up as well due to evaporation. So there's a whole bunch of things that get in your way when you're trying to observe further distances. So it's okay saying go higher, but when you go higher, you then run into the problem of, can you actually see that far? Because if you go to, let's say you go to 50 feet in elevation, right? And the horizon is 10 miles away. The horizon is 10 miles away. It says you can only see 10 miles today, but that's not including the rain. What happens if you can't see that far? You know, this is always the problem we're going to run into. So as much as that makes sense, you're going to get found out in the long run. But what will happen is, when you get days when you actually do get perfect conditions, perfectly flat conditions, like Red Pill Philosophy's done, like I've done in the past, we see a long way, right? We do get conditions like this, right? We do get conditions like this where you can see shore to shore. And when you look at these observations, the observations are across water that are like a mill pond with no ripples on them. There's no effects of any tide. There's no effects of any shoaling. There's no effect of any swell. It is always flat as a pancake, really flat. And when you get these really flat conditions like so, and you can see a very long way, right? That is proof that you're just seeing a long way because nature is allowing you to see that far on this particular day with no physical obstructions. That's it. It's nothing to do with it being loomed up. It has nothing to do with that. You know, we do get these conditions and we do see a very long way. It's as simple as that. There's no demonstrated proof that you can have anything loomed up beyond an Earth curve. There isn't. It's preposterous to even think that. Right, who else have we got in? Esteban Ilbacan, I see you in. Professor Phil Bell, FE cannot have an abrupt horizon. What the hell does that mean? Dangerman, nice to see you in. Oxbow Spirit, nice to see you in. What have we got? How far can one see when looking through an atmosphere of fog and clouds? Exactly, you can't see. It's all dependent on the day. You know, quite often when you actually get these really good observations, these really great observations, it's just a day that you can just there's not a lot of crap in the air, and you've got flat water, and that's it. Are you going to address the errors in the lighthouse observation? I think I've already done that. Do you know what, dude? You're like the worst troll. So goodbye, mate. I don't need you in today. Right, who else have we got in? But yeah, I actually went back and I actually went to 19 miles away. I didn't stop at 13. I went to 19 miles away, and I saw the lighthouse from just 4 feet above actual sea level. I don't need to address any observation at 13 miles that I put out. I went to 19 miles. I went to 19 miles and I saw it from there. Check the video. Julie Bennett, nice to see you in. Musicians for Truth, nice to see you in. Right, okay, so essentially that's all I really wanted to say today. I wanted to do this little presentation. I've been working on it for a day and a half or so, just getting everything together, all these calculations in order to show you. Obviously, what I would say is that as flat earthers, we need to start using these Shoaling calculators from now on. And what you can do is if you go onto the refraction site, you can actually change it, and you can go onto the steep side, and you can calculate it, and it gives you basically what the heights are in when it's steep, etc., rather than just being moderate. So you got shoaling, you got refraction, breaker types, the wave setup. There's all kinds of stuff that you can use, but we can demonstrate this. This isn't an Earth curve calculator that's just absolute ramped up nonsense that just gives you the illusion that you're seeing further than you should because you just changed the refraction limits on it. No, this is actual research that can demonstrate the properties of a wave and how it affects the wave heights. And all you need to know is what is the topography of the land underneath, and then you've got an idea of how steep the beach is, and then you can just put these calculations in and you can get yourself a shoaling height, which quite often, if you're at the shoreline, is going to be far bigger and far higher than your eyes are, that's for sure. Right, okay, so thank you everyone for stopping by. Wow, I've been going for nearly 40 minutes now. And yeah, I think that's it. I think I might do a live stream tonight if I can get hold of Tony. Want to reveal who won the Triggered Earther of the Year award. That should be fun. If I can, I'll do it today. If not, I'll do it tomorrow. And thanks everyone for stopping by, and I'll see you all in the next one.